I want to demonstrate the insecurity of the Staples Android app here, and I notified them more than 4 months ago, and they don't appear to have any intention of fixing it. I think all I got was an automated message that promises to fix it, but when I tried to contact them again, they ignored me, so there's no reason not to go public. This is an emulated Android phone running in a VirtualBox, the Genymotion emulator, and if you run the Staples app, it connects to the retailer, and you can create an account here. And so if you create an account, I can do anything I want, and I'll put in a password of PADSSW0RD, which is an old Microsoft password that is passes most tests of sufficient complexity. So now the app knows that I have logged in, and I could even save addresses and credit cards and stuff in here. And the question is, how does it know that I've logged in? Now, if you start the app later and they don't want to keep making you log in every time, they have to store some kind of credential on the phone. And the best thing to do is store some kind of cookie, a random number on the phone that means something only to Staples and nothing to anyone else. But if you make the unwise decision to store a password in your Android app, there are recommendations, and here's one of the many examples of this. You could store it using asymmetric keys and then fetch the key from the server every time, and that would be very secure. Nobody would be able to get it without satisfying some requirements, although I'm not sure what requirements you'd have to get the key. There is an Android key store provided by Google in Android, designed just for this purpose, which is the obvious good place to put it. Or you could store it with your own custom encryption, or with no encryption at all. And what Staples has done is make custom encryption, and in general, custom encryption is a terrible thing to do, because encryption is harder than most people seem to understand, and they try to implement encryption, and they can't do it right. So I think I'm going to do this with 2 videos. I'm going to show you first how I detected that there was a problem, and then in more detail how to steal the data off the phone that's stored by the Staples app. So the first question is, what kind of data is stored on the phone? And you can find that out with the Android Debug Bridge. If you just get a shell on the phone, then you can look here, and every app has their own folder to put data in, and here's where Staples puts their stuff. So if you just look in there, there are a variety of files, and after hunting around a little with grep, in fact I can just do it that way here. If I just grep -ir for password in a current directory, it will find that in the shared preferences folder there is a thing called encrypted password. And so now the question is, how strong is this encrypted password string? It doesn't look very long, and it's base 64 encoded, so you might wonder, how bad is this? Now, it's not as simple as just being a base 64 reverse string, but here's a cute trick I learned from going through the Web Applications Hacker's Handbook. If you suspect that people are doing something foolish in encryption, and I do, since they really should put this in the keychain, it shouldn't even be here at all, that suggests that they don't know how to do things right, or they don't care. So the thing to do is to make an account with a password that contains a lot of repeated characters. So I'll make testsam4. Now I'm going to put in like Q, 1, 2, 3, 4, 5, 6, 7, 8. So I have 32 Qs, and then I put in some numbers and capital letters just to pass their complexity requirement. But the first 32 characters of my password are the same. Now, oops, I hit the login instead of create an account. Let me fix that. Okay, and it's all right. That should create an account with a password that starts out with 32 identical letters. So now, if I do the same thing here, you'll see the encrypted password is now quite a bit longer. And the question is, does this password repeat? Because if it does, then they're using the textbook encryption called electronic codebook mode, which is inappropriate for production environment. Now you can see this starts with BX, and there isn't another BX later, so it's not so bad that the actual base 64 string itself repeats, but base 64 is grouping the bits 6 at a time, so it can fail to repeat even though the actual underlying binary is repeating, and that is of course the case here. So if you go to any tool, you could do it with Python or anything, but you might as well just use an online tool. I'm just doing it to make it easy for everybody. So this online tool will turn base 64 into hexadecimal, and when it does, it comes out as this. So then the thing to do is just throw that in a text editor so you can play with it. And I'll make it bigger, and then I'm just going to see if there's a repeated string here. There's a 05, and there's the other 05. So right there you can see this is the encoding of the first 16 Qs, and this is the encoding of the second 16 Qs, and this is the encoding of the 123A. So it is just taking the raw input and encoding each block of input to a separate block of output without adding any varying nonce before doing that. And this is a very common mistake in cryptography. It affected Microsoft twice in different products. This is what happens if you just take someone who doesn't understand cryptography and tell them, encrypt this book by next week. They will just look it up in something like a math book and implement the simplest mode and not realize that this is really serious. And so I'm going to stop here at this point for this video, and I'm going to make a second video of the details of how you actually steal the data off this device. But this already tells you that they've made custom encryption and they have done it poorly. So it should be pretty easy to crack. And it's going to turn out to be pretty easy to crack. So I'm going to stop this one.